Hello AP Statistics students. In this video, we're going to take a look at how to use the normal model to make predictions about possible sample proportions using their sampling distributions. We saw in our last lesson that there are some conditions that need to be met, but when those conditions are met, our sampling distribution is normal. And so we can use our normal CDF probabilities to make predictions about where a sample will probably lie. So let's do this. Shouldn't be too hard. The setup of this is mostly the difficult part. Actually using a normal CDF is, of course, pretty easy. So here's our scenario. Going to college. A polling organization asks a simple random sample of 1,500 college students, first-year college students, how far away from their home they are. Suppose that 35% of all first-year students attend college within 50 miles of home. All right, that is our population parameter. All right, so we kind of already know the actual true proportion. 35% of all first-year students attend college within 50 miles. Find the probability that the random sample of 1,500 students will give a result within 2 percentage points of the true value. So our sample might not give us exactly 35% being within 50 miles of home because of sample variability. But what are the chances that it's within 2 percentage points? Now this one threw me off a little bit at first because, well, they're asking them how far away they live. But then they're getting the proportion that are within 50 miles. So yes, the respondents would say, hey, I live 30 miles from home. Or I live 30 miles away. I live 20 miles away. I live 2 miles away. That's what their answers would be. But then from our sample, we are calculating p-hat. What we're actually interested in is the proportion within 50 miles of home. So with our sample, we then calculate the proportion that are within 50 miles of home. Okay. And we want to know how close is our sample to what we know is true, the 35%. All right, what are the chances that we're within 2 percentage points? So our overall goal is we want to know the probability that our p-hat from our sample is within 2 percentage points. So is it bigger than or equal to 33%, so 0.33, or smaller than or equal to 37%? All right, we want to find the probability that we are between 33 and 37% within 50 miles of home. All right, well, that's going to, hopefully you can see how that's setting up our normal CDF. We have our lower and our upper. We just need the mean and the standard deviation. So here's where the setup comes into play. What's our mean? Well, we did that in our previous lesson, didn't we? The mean of your sampling distribution of p-hat, of your sample proportion, is going to be the true population parameter, the true proportion, 35%. All right, that's what we learned in our previous lesson. The center of a sampling distribution is on the population proportion. So if I want to visualize this, I could start drawing my sampling distribution over here of p-hat. I now know that it is centered on 0.35. Now, what shape is it? Hopefully it's going to be normal, right? But we don't know for sure it's normal yet until we check some conditions and we take a look at the standard deviation. So the next thing probably is to do the standard deviation. So what is the standard deviation of p-hat? All right, so that is that one formula we looked at. It is the square root of P times Q, so 0.35 is our parameter, times Q, which is the other half, for lack of a better word, 1 minus p, which is 0.65. All right, I like the PQ explanation there, divided by our sample size. What was our sample size? 1,500. So we type that into the calculator here. So 0.35 times 0.65. I like to do the order of operations here. Divided by 1,500. And then I have to, oh, that's an ugly number, but I have to square root that number. So square root second answer. All right, hit enter. 0.0123, that's kind of convenient. 0.0123 is our standard deviation. Now, when we do that calculation, we do have to give a nod to the fact that there's a condition on that calculation, okay? That is only the standard deviation if we are sampling less than 10% of our population, okay? So we are making an assumption right now. We are assuming that our sample of 1,500 students, I guess I should even say first year college students, is less than 10% of the population. What is the population of all first year college students? And I think that's a safe assumption because we're not looking at just one college. That might be a dangerous assumption if our population was the first year college students at one college. But we're looking at all colleges. And so it's pretty safe to assume that 1,500 is less than 10% of all first year college students, even if you just look at the US. So that is while it is an assumption, it's a pretty safe assumption. So we do have to give a nod to that idea every time we calculate the standard deviation. All right, so if I wanted to over here, I could do plus 0.0123 over and over again, right, to get my standard deviations. And I could do minus 0.0123, and I could get my standard deviations this way. I don't really want to do that, but if you remember drawing the normal model, that's oftentimes what we did. All right, now I've got to verify the shape. Yes, I definitely hope and want this to be normal, right? Because then we can do math. If this is not normal, we can't do math. So this is the large numbers condition. The shape will be normal if n times p is greater than or equal to 10 and n times q is greater than or equal to 10. So we just have to quick do that math. So my n is huge, 1,500 is my sample size, times p, which is 0.35, and then 1,500 times q, which is 0.65. Hopefully both of those numbers are greater than 10, which they of course are, but we'll do the math anyways. 1,500 times 0.35 is 525, and 525 is definitely greater than or equal to 10, and 1,500 times 0.65 is 975, which is also greater than or equal to 10. So what we have here for our shape, the shape of this sampling distribution is normal, or I guess I should technically say approximately normal. Because n times p is greater than 10 and n times q is greater than 10. I think I should technically say greater than or equal to, but I'm not sure how to type that in right now. But yeah, I probably should put the equal sign underneath those alligators. All right, and so we did the math, so we know this shape is approximately normal. We have now done all of our assumptions, our conditions to make sure that we can now do a normal CDF. All right, so again, we want to know the probability that this p hat is somewhere between 0.33 and 0.37. All right, after all that, it's easy to forget what the heck we were doing. I want to know the probability that this sample of 1,500 first-year college students will give me somewhere between 33% and 37% of them being within 50 miles of home. So that is simply now going to be a normal CDF. Our mean is equal to 0.35. All right, we got that from up here. The standard deviation is going to be equal to 0.0123. We got that from our calculation there. The lower is 0.33. And our upper is equal to 0.37. So all we got to do now is throw that into the calculator. Second distribution, normal CDF, lower 0.33, upper 0.37. Our mean is 0.35, and our standard deviation is 0.0123. Hit enter a bunch of times, and you get 89%, 0.896. So, to sort of interpret that answer, there is an 89.6% chance our sample of 1,500, I'm running out of space here, first-year college students will give us a proportion between 33% and 37% of students living within 50 miles of home. That's what our answer means. So again, hopefully the math isn't too bad, right? It's just a normal CDF. But you do have a couple of steps, okay? You got to calculate the standard deviation. You have to, when you do that, you have to do this assumption that you are sampling less than 10% of your total population. Not sure. And then when you want to make sure this is normal, you have to do the n times p and the n times q to make sure that, yes, those are both greater than or equal to 10, meaning you've sampled enough people to make your sampling distribution normal. All right, let's do one more here. Maybe you want to pause the video, try it out on your own real quick. Can you do those two assumptions as you calculate? But hopefully this one will go a bit faster for us now that we've seen it in action. All right, if you're just along for the ride, let's do this. Suppose we've done this problem before, but now I added a question to it. So again, 84% of students at a large high school regularly use a backpack to carry their books from class to class. Imagine taking an SRS of 100 students and calculating the proportion, p hat, of students in the sample who regularly use a backpack. So obviously, hopefully that there's sample variability. This sample is not going to give us exactly 84% using their backpack. It's going to give us hopefully something close. So I want to know, what is the probability that that SRS of 100 will give us a proportion within 5% of the true proportion. So I want to know the probability that this p hat from our sample is within 5%. So that's all the way down to 79% and all the way up to 89%. What are the chances there? So we have to calculate the mean, the standard deviation, our assumption on the standard deviation, the shape, the condition for the shape is met, then we can do our normal CDF. So the mean of our sample proportions, of all the sample proportions, will be centered at 84%, the actual true proportion. Okay, and then our standard deviation of p hat is going to be equal to the square root of 0.84 times 0.16 p times q divided by n, which is 100. So what do we get here? So we have 0.84, times 0.16 divided by 100, and then we have to square root that answer. 0.0366. 0.0366. All right, but remember we have our condition here. We are assuming that our sample of 100 students is less than 10% of, now what was our population? At 84% of students at a large high school. So we're actually only looking at one high school. Is less than 10% of this high school. Now, is that a valid assumption? Yeah, because 100 is 10% of 1,000. So is it a reasonable assumption to say that this high school is more than 1,000 kids? That's not unreasonable. Edison's like, what, 2,500? So we're all good. Next, we need to know the shape. Is the shape normal? So we have to test n times p which is equal to 100 times 0.84, which that is definitely, well, that's just 84, which is definitely greater than or equal to 10. And n times q, which is 100 times 0.16, which is, well, 16. We can do that in our head, which is also greater than or equal to 10. So we have now verified that we do have an approximately normal shape. The sampling distribution of p hat will be approximately normal because n times p is greater than or equal to, I'll do it that way, that's not the greatest way to write it, but, and n times q is greater than or equal to 10. All right, now we have met all the conditions to finally use our normal CDF. So instead of rewriting, I can just go up here. So now we can do the normal CDF, where our mean is equal to 0.84. Our standard deviation is equal to 0.0366. Our lower is equal to 0.79, and our upper is equal to 0.89. Type all that in. Distribution, normal CDF. So lower, 0.79, 0.89, 0.84, and 0.0366 for our standard deviation. 83%, 0.83 I'd say. So there's an 83% chance that this SRS of 100 students will give us a proportion between 79% and 89% of students using their backpack. All right, I hope that kind of makes it clear how to use a normal CDF approximation to figure out and make predictions about possible sample proportions using a sampling distribution.